So at this point in time, the people up here can go and get a nice comfortable seat. And Nick, I'd like you to come up to officially start our presentations. I met Nick about a year ago. I mentioned that TerraPower held 2 pre-conferences to kind of get ready for this. This one in Annapolis, Nick was really kind of the prime driver, although Ludwig set it all up. It's all his fault. No, it's really. Anyway, Nick is, some of you know him well. He is worked at Oak Ridge National Laboratory. He's the head of the medical and technical director for the Radiation Emergency Assistance Center at Oak Ridge. But he's always been associated with Yale, and now he's back at Yale as a clinical professor of medicine in the Department of Therapeutic Radiology at Yale University. So with that, Nick, it's all yours. Give a big hand to Nick, all right?
Thank you very much, Alan. Notice Alan reminded me of the time. So we're 5 minutes ahead of schedule. I'm honored to chair the opening session today. And as the chair, my goal is to provoke some scientific interactions as well as to keep us on schedule. Or schedule. And so I think we have an exciting first program. I think it's going to be provocative, and it'll provide some helpful shaping of our thinking for this week. The first speaker on the program is David Brenner. And David, as you know, is at Columbia University, the Center for Radiological Research. And he and David, if you can start walking up, that would be great. He is also the PI of the Center for High Throughput Minimally Invasive Radiation Biodosimetry, which is a multi-institutional consortium to develop high throughput biodosimetry to rapidly assess dose. David's research is focused on mechanistically based models for the effects of ionizing radiation on living systems. His research addresses both low doses as well as high doses of radiation. David's received several awards, including the Radiation Research Society Thalia Medal, as well as the Oxford University Weldon Prize. He is a member of the U.S. National Academies of Nuclear and Radiation Studies Board, and I am delighted to introduce him as our first speaker today. I think you'll find his talk to be very informative. David?
Thank you, Nick. So, what a pleasure to be here, and so congratulations to the organizers. This is terrific. So I was asked to talk about at least what I perceive to be the strengths and weaknesses of the linear extrapolation from risks that we know to risks that we don't know. So question one is, well, what risks are we talking about? And as everybody knows, at least at higher doses, all of these things you can see epidemiologically. But I'm going to focus on radiation-induced cancer because I think in the big picture of things, that's the most important effect for us at low doses. Okay, this is my view of the problem, the issue. So this is a graph of radiation-induced cancer risk as a function of dose. And so the epidemiologists in the audience work really, really hard to come up with some data points at high doses. But as soon as they do that, they're asked, well, what about at lower doses? So they work really, really, really hard and come up with some data at lower doses. But as soon as they do that, they're being told, well, we really need doses that are much, much lower still. So ultimately, radiation epidemiology can guide us, but can't really give us the answers at the low doses that we're really interested in. So you could ask, well, how low actually can the epidemiologists go? And to answer that, by and large, you look to the survivors at Hiroshima and Nagasaki, and we're going to hear more about those as the meeting goes on. So this picture here, each brown dot is individuals exposed between 5 and 100 milligray, And there are a lot of those, there's 25,000-ish of those. So the A-bomb survivor study, really, in my picture of things, is a low-dose study, not a high-dose study. Well, I guess it's a high-dose study also, but our interest is in the low doses. So, as you know, there have been lots of reports, and this is the latest of solid cancer incidents from the A-bomb survivors. And can you read this? I can barely. Oops. Okay, I'll read it here. The lowest dose range that shows a statistically significant dose response using the appropriate models was 0 to 100 milligray. So 0 to 100 milligray, that's sort of the dose range. But people argue about this number a lot. And just maybe it's 0 to 200, and maybe it's 0 to 50. I don't think it matters too much. But this is certainly the ballpark dose range where you can see epidemiological data effects. And that's backed up with other different studies. This is the big UK CT study looking at leukemia as an endpoint. And again, in the same dose range, there's just about a dose response curve. So again, you can argue exactly where you can see effects, but it's somewhere in this range of tens to hundreds of milligray. So epidemiologists are smart folks, and they work really hard. How come they can't go to much lower doses? Well, I think, at least from my perspective, the reason is simply the signal-to-noise ratio. 40% of the people in this room are going to get cancer. So to look for a very small increase over that 40%, well, that's very hard indeed. And what it means is the sorts of studies that you need to do to look at low doses become progressively harder and harder as the doses get less and less. And yeah, this is a classic graph that's, well, you can see it in various different places. But basically, as you get to the doses that we're interested in, the sorts of sample size that you need absolutely blows up and becomes enormous. It gets to the tens of millions, and so obviously that's not practical. So there is a limit, at least in our current epidemiological framework, as to how low you can go in with conventional radiation epidemiology. And just give one slightly flippant example of what happens when you get near that, where the noise really starts to overtake things. 3 studies of mortality in radiologists over the years. One of which shows a statistically significant increase, one of which shows a statistically significant decrease, and one shows no significant change. So once you get to the noise, you can really get more or less any result that you want. So you have to be careful about cherry picking the data that appeals to you once you get down to these very low doses. So we clearly want to go to doses much lower than the epidemiologists can give us. And again, this is the problem. We have data at comparatively high doses. We want to estimate risks at much lower doses. So you can put any line you like that goes through the origin and goes through the data. You can have linear, or you can have threshold, or hormetic, or curvilinear. So what I'm going to talk about is exactly this. What curve makes sense? And what's used, as everybody in this room knows, from a radiation protection point of view, is a linear no threshold model to extrapolate those data to the origin, a straight line. And what I'm going to talk about is the biophysical, it's usually called the biophysical argument, that leads to this linear extrapolation. I'll talk about what it is, and I'll talk about its strengths, and I'll also talk about its weaknesses. Okay, so it is a biophysical argument, so we're going to talk biophysics for a moment. So I'm going to talk about the number of photons per cell nucleus at different radiation doses. So these ellipses are my picture of what a cell nucleus looks like. And at a gray, 1,000 milligray, actually you get lots and lots of photon tracks or secondary X-ray tracks going through a nucleus. So hundreds and hundreds of them. So let's go down in dose by a factor of two orders of magnitude. So we've gone down from 1,000 milligray to 10 milligray. And what happens is that obviously you get less and less tracks going through cells. And somewhere in the, depending on the particulars of the X-ray radiation, somewhere around the 5-10 milligray dose, you're getting to an average of one track going through individual cell nuclei. So it's Poisson distribution, so you'll have some nuclei with no tracks going through them, some with one, some with two, and so on. And that's this picture here. So let's go down again in order of magnitude, one further order of magnitude. So now we've gone down from 10 milligray to 1 milligray. So what happens when you go from 10 milligray to 1 milligray is not that the damage changes, because already we're at the minimum damage that a cell can feel, which is a single track going through a cell nucleus. What happens as you go to still lower doses is simply that less cells feel that same damage. So basically going from the 10 milligray to the 1 milligray, a tenth of the cells are going to feel any damage at all. But it will be essentially the same damage. It'll be a single track. And that's very different from the story at 1,000 milligray, where the damage is very different from 10 milligray or 1 milligray. But the point is that 10 milligray and 1 milligray, it's the same damage, just less cells feeling that same damage. Okay, so now let me talk again in these three dose ranges. What are the radiation-induced cancer risks as far as we know at these different doses? Well, at 1,000 milligray, gray, I don't think anybody's going to argue too much that you can definitively see an increase in radiation-induced cancer. So I'm going to put an arrow there, and I'm going to put that cancer sign next to it. So let's go to 10 milligray. So at 10 milligray, we're really at the limits of what you can do epidemiologically. So I'm going to tilt the game a little bit in my favor here by looking at a situation where we know that there is going to be high sensitivity. So again, what are the known cancer risks at this dose? So I'm going to look at the Oxford Survey of Childhood Cancers. So as probably most of you know, in the 1950s, it was pretty common to give an in utero X-ray to pregnant mothers. Yeah, I asked my mother if I got one, because I was born in the early 50s, and she said, yeah, absolutely you did, but it was a bit blurry, so they gave me another one. So take everything I say in that context. So the mean dose in this huge study was 6 milligray. So this is the ballpark we're interested in. And because we're stacking the deck in our favor, because we're looking at childhood cancers, and childhood cancer is pretty rare, so the signal-to-noise ratio is going to be more in our favor. And the biggest study, the Oxford study, looked at 15,000 case control pairs and did in fact come out with a statistically significant increase in childhood cancer risks. Again, for this mean dose of 6 milligray. So in most situations at this dose, you really can't see anything above the noise. So I'm stacking the deck here by looking at childhood cancers where the signal-to-noise ratio should be better. So coming back to our chart, I'm going to put at 1 milligray, at 10 milligray, I'm going to put a little arrow because clearly the risks are smaller, but I'm going to make the claim that risks at this dose are demonstrated. So now the question is, what about at 1 milligray? So big question mark here. And clearly we are now in the dose range where you can't do epidemiology in any realistic way. So this is now the place where we have to extrapolate from higher doses. and this is the crux of the LNT argument, that as you go from 10 milligray to 1 milligray, all you're doing is changing the number of cells that feel the same damage. You're not changing the type of damage. Now, if you're trying to extrapolate from 1,000 milligray to 10 milligray, well, that's a different and harder story, in my view, because you're going from different types of damage, as you can see in the two left panels. But as you go from the middle panel to the right panel, it's the same damage. It's exactly the same damage to any given cell nucleus. All that changes is the number of cells that feel that damage. So that is, in a nutshell, the LNT argument. As you go down, once you're in the single track regimen, as you go down, say, from 10 milligray to 1 milligray, the risks should presumably just be dependent on the number of cells that feel damage, because the damage is the same. There's no difference in the damage at 10 milligray and 1 milligray. So if I can put that another way, in terms of a chart of cancer risk against dose, at high doses, well, there are lots of other models to be thought about there, but this sort of extrapolation really doesn't work. And so you can have all sorts of different dose responses at higher doses. But there is a tipping point, and I've made a yellow and green division here, correspond to a mean of about 1 photon per cell, and that's somewhere in the 10 milligray range, where below that you could absolutely expect a linear dose-response relationship, because you're simply damaging fewer and fewer cells as you go to lower and lower doses. So this is the LNT argument, I think. Doesn't apply to high doses. It applies only in the really low dose range. So you might expect at higher doses different mechanisms, because as you saw, you get different types of damage. But in the yellow region, the type of damage is the same. It's just the number of cells feeling it is different. Okay, so that's the argument. As with any theoretical argument, it's got a lot of assumptions built into it, which you can certainly question. And I'll talk about a few. I'll talk about the issues of DNA repair, talk about issues of immunosurveillance and cell-to-cell communication, which I think is probably the most important. So DNA repair, well, yes, we've been exposed to ionizing radiation for an awfully long time, and we indeed have developed incredibly efficient DNA repair mechanisms. I mean, it's just staggering when you think about the amount of damage we get every day and the amount of repair that's needed. But whenever you get DNA repair, there's always the possibility of DNA misrepair. And ultimately, I think that's what cancer is all about. It's radiation damage and that damage being misrepaired. Immunosurveillance. So the argument might be that, well, we're talking about really small amounts of damage here, and we have great immunosurveillance in our bodies, as we know. Surely it could mop up that small amount of, those small numbers of pre-malignant cells. Well, yeah, if that were so, you'd wonder why anybody would ever get cancer, which ultimately starts from a single damaged cell. And in fact, there's evidence, there's data against this idea that you can mop up small amounts of damage through immunosurveillance. So there's a phenomenon which has different names in the literature. I like sneaking through as a good name. So what's being done in this experiment is they are injecting different numbers of mastocytoma cells into appropriate mice, and then counting the number of mastocytomas in the mice. So starting from the right-hand side of this graph, when you inject a huge number of mastocytoma cells, indeed 100% of the animals get mastocytomas. And as you decrease the number of cells that are injected, you get, as we move to the left, we get progressively fewer and fewer mastocytomas produced. But as you get down to very low numbers injected, it doesn't actually go to zero. It's sort of, within the limits of these data, it kind of flattens out. So this would imply at very small numbers of in our case, pre-malignant cells, immunosurveillance can't pick up every single damaged cell. Okay, and the third, and I think the strongest argument against the biophysical argument is intercellular communication. So the argument that I outlined before really depends on the development of monoclonal tumors starting from a single cell by independently developing cells. So the cells are not talking to each other in this model. And of course, we know that the whole process of carcinogenesis, cells talk to each other, and the local microenvironment is pretty key. So that's undoubtedly a weakness of the biophysical argument. But I mean, just saying it's a weakness doesn't help us much, because we want to know, is it a big weakness? Does it mean that the risks are higher? Does it mean the risks are lower? And that's hard to say. Yeah, cells do talk to each other, but what's the implication of that? Well, in our field, in the radiation biology field, by far the most quantified intercellular communication effect is the so-called bystander effect, which I'm sure most of you have heard of, where a damaged cell can produce damage in a neighboring non-damaged cell. So this cell-to-cell communication of radiation-induced damage. And broadly speaking, when people have quantified bystander effects, they've always got curvilinear, downwardly curving dose-response curves, like this one here. And so, I mean, if this bystander effect was the cell-to-cell communication of interest, well, if you extrapolated from the highest dose down to the origin, actually you'd be underestimating the radiation risks using a linear model. But of course, we certainly don't know if bystander effect is a relevant cell-to-cell communication phenomenon in this context. So the bottom line, as far as I can see, is that the biophysical argument, which leads to a linear no-threshold model, is certainly quite plausible, but it does rely on assumptions about single cells which act independently of each other. And we know that's not fully correct. But I think at this time, what we don't know is whether deviations due to cell-to-cell communication are going to be big, going to be small, or even which way they'll go, whether they're going to increase low-dose risks or decrease them relative to a linear extrapolation. Nevertheless, with those caveats, let's talk for a moment about a straight line relationship between radiation dose and risk. Yeah, so the implication is that as you lower the dose, you proportionately lower the risk at low doses. So at very low doses, what that means is that the risks are going to be correspondingly very low. But it also means that there is no dose at which the risk is actually zero. So in that context, should we worry about small doses because we know that there are small risks associated with small doses? So let me give you this example to try and stimulate everybody's thinking. Let's think about some activity or other, which is a low-risk activity. So the risk of harm to an individual is, say, 1 in a million. So very small individual risk. So if I was faced with a risk of 1 in a million, I certainly wouldn't worry about it. And now supposing we have a little breakout session and there are 100 people that are going to be exposed to this activity with this risk of 1 in a million. So the chances of anybody being harmed by a risk of 1 in a million in a group of 100 is essentially zero. So when you have a small population and a small risk, there are no public health consequences. But now let's take the other end of that coin. Supposing there's a population of 100 million people who are exposed to that same activity with an individual risk of 1 in a million. Now, in this situation, it's certain that some people in the group will be harmed, even though the risk you might describe as negligible in terms of individuals. What comes into play here is the distinction between an individual risk, which is negligible and can be ignored, and a population risk, which really depends on how many people are exposed to that risk. So if 100 million people are exposed, the risk will be actually real in the sense that some people will get that harm. And yeah, it's not a perfect analogy, but yeah, look at the lottery. So you buy a lottery ticket, and your individual risk, your individual probability of winning is 1 in some very huge number, so absolutely tiny. So you can essentially ignore the probability that you will win. On the other hand, somebody is going to win, and so at the end of the week on the TV, you'll see some happy person with a large check. So it's not the case that if you have small risks, by definition, you can then ignore those small risks. And I would like to just end by mentioning my really good friend and my really good colleague, Bill Morgan, who really should be sitting in the front row shaking his head at me. So he was the person who actually asked me to attend this meeting, and maybe it was the same for some of the other speakers. He was a good guy. He was smart, and he was open-minded to different points of view, politically savvy, and a great pal. And I miss him a lot, and I'm sure lots of other people in the audience do too. So thank you for your attention.
Thank you. Thank you very much, David. Provocative, as I indicated. We have time for a question or two. If you want to just come up to the microphone. As you do that, let me ask a quick one, a simple one. You know, Jacques Bouchard gave a interesting lecture at the NCRP meeting a few years ago where he talked about prudence. And as regulators do their job every day, prudence is a societal value, not a scientific measurement or scientific evidence. How do you take your observations and your thoughts and move them or link them with a societal value such as prudence when you're setting regulations? Or you can just answer that in about 5 seconds. That would be great. Thanks.
Well, I suppose one thought I did have is that I mean, it's assumed that linearity is a pretty conservative assumption. I'm not sure I see that. I mean, that linearity may be a reasonable assumption. Linearity may be underestimating the risks, or linearity may be overestimating the population risks. But I'm not sure how you would operate a radiation protection system in any other way. So I think it's reasonable. I couldn't say that it's prudent, but I think it's reasonable.
Okay, good. Risk benefit may wind up being a topic. Yes.
Hi, I'm Ben Greenspan. I fully disagree with your comment about the risk with a large number of people. I think that's the wrong way to approach this. And for example, if Bernie Cohen, as you know, made a list of 1 in a million risks, and one of them was smoking 1 cigarette. So if you took 1 million people who were non-smokers and had them all smoke 1 cigarette, do you think any of them would get lung cancer from that 1 cigarette? I say no. So I think that's the wrong way to apply this.
I mean, when you talk about a risk of 1 in a million, you have to tell me what you mean by that. As far as
getting lung cancer from 1 cigarette.
Well, in general, if you talk about a very small risk, 1 in a million, I mean, that means that if 10 million are exposed to that risk, 10 people will get the effect. That's just the definition of a small risk. And you can argue that if it's a small risk, it's no risk. But I think what I showed was that a small risk applied to a very large population will give you some effects.
So it's
the law of large numbers, essentially.
Yeah, I understand what you're saying, but I disagree with the application.
It's about risk-benefit, and looking at the benefit of cigarette smoking, these people have the opportunity to get chronic lung disease. So, point well taken. Next.
Thank you.
Hi, I'm Mohan Das. I have many points with which I disagree, but I'll get to present my point of view tomorrow in my presentation. I just want to mention one thing about needing large numbers of cohorts to study low-dose risks, like millions of people. In reality, smaller cohorts like 10,000 or even 5,000 have shown reduction of cancers that are measurable. And so the statement that you made that you need huge cohorts to study low-dose risk reliably is based on the LNT model, not based on actual data. Actual data shows reduction of risk from low radiation doses. So there you don't need millions of people. You can measure with tens of thousands of people.
Well, I look forward to your talk. There have been a fair number of low-dose studies where risks have been seen, like the CT studies.
Very good. Thank you. Next.
Hi. You presented data on the mastocytomas as a point about immunosurveillance. Do you think it says anything about the neighbor effect?
Well, that wasn't a radiation study. That was simply injecting different numbers of a model for a premalignant cell and reducing the number of premalignant cells to a very small number, and wondering whether indeed immunosurveillance could remove those few premalignant cells.
So it's not an effect that you think happens with other cancers?
Sorry, I didn't follow that question.
So the neighbor effect is not something you think that happens with other cancers?
The bystander effect, interesting. It's never really been demonstrated in the radiation-induced cancer world. It's been demonstrated in the radiation-induced chromosome aberration world, the radiation-induced mutation world. It really needs to be studied in the radiation-induced cancer world, but really hasn't.
Next.
Hi, I'm Jerry Cutler. I think you got the whole model all wrong. This tying everything with radiation is, well, I think it's a myth. I'm being polite.
That's a good start, Jerry.
The big problem is we're breathing air, we're breathing oxygen. The oxygen's doing enormous damage to our cells. We're not accounting for that, and so all these models and all these ideas are just not relevant. You're in the wrong ballgame.
Well, I think I was talking about radiation-induced damage. I think when you're talking about environmental damage, that's interesting too. But
yeah, radiation, our bodies are 75% water, and of course, radiation does some radiologists. Breaks up the water molecules, and so there's oxygen coming from there. But that's totally negligible to the oxygen we're breathing. We use it, of course, to burn glucose, but it damages all the biomolecules, and so you're just down the wrong track.
Okay, more later. Last question.
I'm Ruth Weiner, in case somebody doesn't know. I deal with transportation risks, and in estimating those risks, we look at the miles traveled, the number of accidents per mile or kilometer traveled, which is using a frequency as a surrogate for a probability. And I really would like to see, I'm not advocating anything, but I really would like to see how that notion translates when we talk about low doses. Frequency is not a probability. It's the way we measure a probability. And yet, this is the application. And I hope to see people somehow commenting on that.
well, at these low doses, we can neither measure frequencies or probabilities.
That's true, but we do it. I mean, if you...
No, we don't. Not at these doses.
No,
absolutely
no,
we
you
don't.
don't as a biologist. But when you start to look at the comparison that everybody uses for risks in transporting radioactive materials, which is what I do, and the comparison is always, always how many accidents are you looking at? And that's frequency.
Okay, very, very good. I think you made your point well. We have to move on. Thank you very much for the questions. They were really good. David, that's a great start. Our next speaker is Roger McClellan. Having read his CV, I am really humbled by the contributions that Roger has made. He moved to Richland in 1944 with his parents, to join his parents. Obtained a degree as a doctor of veterinary medicine in 1960 from Washington State University. Studied in the area of the effects of internally deposited radionuclides. He has been the director of the Lovelace Inhalation Toxicology Research Institute from 1966 through 88. President of the Chemical Industry Institute of Toxicology, and served on the NCRP Council for 30 years. And Roger, it's a real pleasure to introduce you.
Well, thank you very much. It is a real pleasure to be back here. I say back here because 74 years ago and about 2 months, I joined my parents here. I had the good fortune that there were many wonderful people, bright, industrious individuals that arrived about the same time. One of those was Herbert M. Parker. I'm very pleased that I then later had the opportunity to work under him. Well, yesterday, I've been on a kind of a sojourn. My wife and I came to the Northwest a week ago Saturday for her 60th high school reunion in a little town near Olympia. That was a great experience. We've been visiting family and familiar haunts and enjoying good food and good friendship. We were involved in an event on Saturday. It was Washington State against Utah, and that's an element of probability, I'll have to say. So we went in that fourth quarter, I thought, God, I hope they don't coug it. Now, for you who don't know that phrase, the Washington State are the Washington State Cougars, and for a period of time we had a dismal record in terms of football. We could coug it. We could be ahead by 3 touchdowns in the fourth quarter and coug it, lose it. So I understand probabilities. Well, one of my principal mentor was the late Leo K. Bustad, and he went on, was dean at Washington State for a period of time, a very distinguished career. As he used to say, Pullman, Washington is not the end of the earth. We have a lot of clear weather, so we see the end most days. So it's a long drive from Pullman down here. So I had a lot of time to think and reflect on people that have gone before us. And I'd ask all of you to think a bit about those giants in the field that really went before us and are not with us today. And certainly Bill Morgan was one of those. So in reflecting that, I thought about the people I worked with at Hanford, and I said, I hope one of them is here, i.e. somebody older than me and wiser. And so I'd like Frank Hungate to stand up. Frank, over here, nudge him. You got to stand up, Frank.
Frank is asleep.
Well, you deserve to take a dose in the morning when you're 100 years old. Frank is 100 years old, and I'm pleased that he was one of my mentors. I actually worked under him in the summer of 1958. So I learned a lot from him and his brother, who was one of my professors at Washington State. Well, let's get going here. I'm going to be actually taking a little different tack on things than the previous speakers, including the organizers. And the central theme is policy and regulation should be informed by science. They're not set by science. I challenge any of you. Give me your algorithm that you use to go from science to policy. And I'm also going to be talking about populations. Here I talk about the public. Boy, I think we ought to take a recess, go down to the local Safeway, and round up some other participants in this meeting. This is not a cross-section of society, I can tell you. We can just look out here, gender, hate to use that word, but old gray-haired men, so gender, age, wow. If you think that you've got a quarter on public attitudes, go out and round up a group of individuals 15 to 25 and see what they look at in terms of the world. So what I want to emphasize is that we've got to take a look at this in a multidimensional way. It's the public concern, ultimately, that we're dealing with. And we have legislation that drives regulations. We have policy choices and science. Now, I'm going to counter Mike and say, I want you to check your personal desired policy outcome at the door. Let's have a discussion about the science first, and then move to the next step in terms of policy choices. This just captures a bit of this. Don Kennedy, who was a very good friend of mine, many years president of Stanford University, was editor-in-chief of Science, and basically he sums this all up, an unrealistic belief that risk can be minimized or even eliminated altogether. In establishing and using radiation protection standards, we have multiple entities involved, and I think we very frequently get this all confused. We're part of, as most of the people in the group here, scientists creating scientific knowledge. That's the scientific community. It's synthesized and used to advise. And so many people in the scientific community are confused about the role of the ICRP, the NCRP. They think they're standard setting. Well, not in a sense. They're advisory. And in the USA particularly, it's really the setting of standards. It's based on statutory authority. And then finally, implementation. In my opinion, I'll be so bold to say, current standards are generally fine. They are appropriate. And when I say that, I talk about numerical standards and I talk about ALARA, which is a foundation in terms of radiation community. Where I think we can do a much better job is in this implementation phase. And that's where the rubber really meets the road. I won't go through all the details of this, but if we go back through the chronology of radiation, the whole first half century was really dominated by tolerance dose, a threshold concept. And I remember some very interesting discussions around that with different people, some shown here. I had the privilege of working at the Atomic Energy Commission when Glenn Seaborg was the chairman. And having some appropriate contacts, I on a few occasions learned when he was going to be in the cafeteria for lunch, and you could actually join him at his table, which was a wonderful opportunity. I'm going to show you a little later a paper that was a figure from a paper published by my late good friend Paul Hinshaw. And I later I first became acquainted with this when I was a summer student at Hanford in 1957, and Bustad said, well, Roger, why don't you give a few lectures on radiation for the technicians? Here's a stack of reprints, help you out. Well, what a wonderful way to get you familiar with the literature. Well, one of those was this paper by Hinshaw. He'd later, for a year and a half, was my office mate in Germantown, Maryland at the U.S. Atomic Energy Commission. But again, I want to just down at the end here, we come to the Manhattan Project and wonderful reminders of last night in terms of at 100B, where the plutonium was produced for that first Trinity shot, and later the plutonium bomb at Nagasaki, and then the beginnings of the Atomic Bomb Casualty Commission. And for those of you who are not that familiar with it, I'd urge you to read a book by Jack Scholl in terms of Song from the Ruins, which recounts his personal experiences there. So Hinshaw described these two fundamental different radiation dose responses, and basically the tolerance levels. That was outlined in a document by Cantrell and Parker, which is very easy for me to remember because it was issued on my 8th birthday, January 5th, 1945. And in that is this schematic rendering, which to the best of my knowledge is the first schematic representation of a threshold versus a linear response. And here we are, 2018, right? 1941. Paul laid this out, and we're still chasing it around the barn. And it applies to a range of health effects. We use the words different times: deterministic, stochastic, probabilistic. So as tolerance dose then began to be replaced by a focus on risk, not dose, but risk. And we moved first through, and there's a great recounts of this by Herb Parker in a couple of his papers as we moved to permissible dose, acceptable risk, and ALARA, and refine the system. We started to move into consequence studies, and these inevitably take you into the world of population dose and population detriment. If we think things have been changing a lot, I think many of you will be able to go back and forth between the different units, but this was from a paper that Mr. Parker put together in September 1960. I joined the staff of the biology laboratory at that time, and I remember seeing several drafts of this paper circulating around the lab. And Herb gave it at the IAEA meeting. And we basically, what I want to just emphasize a point in terms of the congruence between the NCRP and the ICRP. They're basically very similar results. An important piece to bring in is to recognize the role of the Environmental Protection Agency, and I particularly put this because it emphasizes, yes, we live in a world, a sea of radiation. But let's correct that. We live in a sea of hazards. It's not just radiation. And this community, quite frankly, is just stovepiped. You live in a silo. I feel like I'm at a university. You know, those of you who don't get it, that's the physics department's over here, and it's all about physics. And for God's sake, don't cross the street to talk to the biologists, or down the street, talk to the physicians. You might learn something new outside of your field. So this, I can't go into all the details. I'd love to, because much of it involved my good friend, Roy Albert. And when I served at the AEC in 65, 66, the secretary says, that's a GS 1516 desk, Dr. McClellan. I hope you understand the significance. Well, I didn't. I wasn't a bureaucrat. But she said, open the drawer, and it's traditional to put your name, sign it as an occupant of this desk. The first name on that list was Roy Albert. He started in the Manhattan Project and then in the AEC. Well, I want to emphasize this point. We focus a lot on numerical limits and the underlying very elaborate scheme we have of radiation weighting factors, biological effectiveness. I think if there's a serious area that needs re-examination, it's the dose rate effectiveness factor. They're, quite frankly, they're not as rigorously undergirded by science as the rest of it. And I think very important, the overarching optimization guidance. And I say that from a standpoint of working as a scientist, a research manager, a CEO of small companies. Quite frankly, my board of directors would not have allowed me to use anything other than ALARA for all the hazardous agents that we worked with. It was right there. In fact, different wordings of that were in my contract to serve as the CEO of an organization. So when people talk about wanting to get rid of ALARA, I say, holy God, where are you coming from? Well, this just schemats, so we've got a huge body of information from animal studies. Let's take a quick look. You know this data. We're going to go over and over it, I hope, during this meeting in terms of the A-bomb survivors. And it's part of the fact that radiation, ionizing radiation, is the most extensively studied toxicant by far. So I hope as we talk here during this meeting, we occasionally will talk about those other hazards that are out there. I want to emphasize here, I always play this as kind of a little game if I happen to chance on somebody in the media, and particularly if it's a cross-country flight. I ask them, you know, how many people do you think died at Hiroshima and Nagasaki? And then how many people do you think died of cancer? And how many do you think actually died with radiation attributable cancer? They're usually wrong, grossly wrong. I like to try it on my scientific colleagues, and most of them are grossly wrong. They just don't know how radiation is actually a lousy carcinogen, fortunately. But I want to emphasize on this, you know, as a scientist, I learned about t-tests and so on, appropriate controls. I didn't understand the context of the work I was doing. And we're not talking about risk in a sense of absolute risk related to dose. We should always be thinking about it in terms of relative risk. And here's that Japanese data on the solid cancers. Here's just a reminder that as we look at the more recent data, we also see some other diseases popping up. And I do not know the significance of those, because a big challenge in interpreting this data for me is confounding in terms of even in a very homogeneous population like the Japanese. And here, Dr. Mohan's over here in the second row. I think he originally shared this with me. It's just an alternative view of looking at that data. Got to be very careful in terms of keeping track of the scales. Now I want to come to this point, which I think is really the critical one. I found David's talk, as always, extraordinarily insightful, and he appropriately caveated what his position was. But I don't think he gave enough emphasis to the fact that we live in a sea of hazardous agents. So everything he talked about, or most of what he talked about, we could talk about in terms of other hazardous agents, except we typically do not have as elaborate a dosimetric scheme there. So what we're talking about is, in this case, 100 individuals, and we've got the black circles and star. These are the cancer cases for a population. And I would say for this group of people, actually that figure will be higher than that because you're a selected group. We've gone through and you've survived to this point, and by and large, cancer is a disease of the aged. That star is the one that we keep arguing about, right down here. Now, the point I want to emphasize is that star is statistically identified. There aren't any markers of it in terms of that cancer case versus the others. We need to remind ourselves of that, and we ought to be focusing, in my opinion, more attention on all the factors underlying these cancer cases and realize that that star is very important to us, but it's kind of out of context when we shine the light on it, that statistical excess. I emphasize that if we go to a recent document out of NIOSH, and had the pleasure reacquainting myself with one of the people from NIOSH yesterday afternoon, and I hope that they're familiar with this document, but this basically says this is the policy of NIOSH when we look at cancer-causing agents. It's talking about one excess case in 10,000 workers in a 45-year working lifetime. So those of you who think, things ought to go up a little bit, whatever, work through the arithmetic in the back of a small envelope and you'll say, gee whiz, are we out of step with the rest of the working world? And it obviously ends with a recommendation in terms of ALARA. So we have this understanding of late occurring radiation-induced diseases occurring in a stochastic or random fashion. It's very small increase, spontaneous disease, and no unique radiation markers. And I would emphasize, as Mr. Parker would, the epidemiological evidence is a cornerstone of our knowledge, and it's come from studies of human misfortune. The other approaches are valuable, but the cornerstone will be the epidemiological data. And this is a now outdated, but I'm sure we're going to have some presentations. We're going to talk about, induction of mutations. We're going to talk about how we're going to move those along, whatever. If I were to put a current depiction of cancer up there today, it would be a mosaic that would probably have about 200 different points in it in terms of control points, in terms of our current knowledge of the molecular basis of cancer. And so it's going to also have a very strong time dependence element to it, and we really need to understand that as we try to assemble and synthesize information. So my view of current radiation protection standards are consistent with an extraordinary body of scientific knowledge of radiation-induced disease in humans and other species. numerical levels, the overarching use of ALARA are prudent policy choices, informed by the science, not dictated by the science, informed by the science. And standards are informed by a more extensive science base for radiation than any other hazardous agent factor. Let me tell you about one factor that I find very interesting. The relative risk for males is about 1.5 to 2. Now, I'm not talking about 1.015 or 1.02. I am talking about 1.5 to 2, all-cause mortality. Cancer is somewhat lower. What am I talking about? Socioeconomic status, income. The lowest quartile over the top quartile. And in this bias sample here, most of you, I would guess, are in that top quartile. It's great to have income. It's hell to be poor. That's a real hazard. That's a real risk factor that we have to keep into perspective. So with that, let me draw to a close. I'm looking forward to really some very interesting discussions. Again, as I drove down from Pullman, I couldn't help but think back to some of the wonderful Hanford symposium that we had, Frank, over the years. A couple of them we had in the movie theater. We actually put out on the marquee the name of a couple of our fellow scientists who thought they weren't getting enough attention so they could take a photograph and send it to their mother. They did the show on the main stage. So thank you very much, and I look forward to questions and comments following my presentation and throughout the rest of the meeting.
Thank you very much, Dr. McClellan. That was an outstanding introduction for this conference. First question, yes.
Dr. McClellan, my name is Rod Adams. I'm a publisher of Atomic Insights, but before I became a publisher, I was a submarine naval officer. So risk management and risk understanding, and also teaching people how to accept valid risks is part of my training. I enjoyed a lot of what you said, but one of the things that seems to be missing is the fact that if we keep risks from radiation as low as reasonably achievable, where reasonable is relatively undefined, we often increase risks from the alternative to using radiation. In other words, one of the biggest threats to our society's existence today is the threat of climate change. However,
hold it. That's your opinion.
Okay, whatever.
I think there are people who might challenge that.
All right,
but in general, I'll agree with you. Climate change is an important factor, and let me just
or
say,
air pollution, or explosions from natural gas, whatever. What I'm saying is, if we increase the cost of nuclear energy by applying as low as reasonably achievable, and use that as being as low as we can measure, which gets worse every year, we often choose something far less safe as the alternative on a cost basis. That's the challenge we have.
I fully agree with you. And let me say, I fully agree with you, and that's why I'm disappointed this audience is so biased. We're a bunch of radiation experts. We don't have people with those other hazards. We have to look at that bigger world that you clearly understand. And economics is an important factor. I'm probably as disappointed as you that we're 20% of the power in the U.S. is from nuclear. Why isn't it higher? Well,
because it costs too much.
It's economics. I've also worked in the oil and gas business, and I've seen those cycles go. So, yes, these are very complex issues, and I just want to make certain we have a broad view of these.
It's risk benefit, yes.
Yes, I'm Ed Parsons. I'm the Senior Technical Advisor for Radiation Health and Safety here for the Hanford site. I'll also say that I'm a certified instructor in the Claire Graves modeling for cultural development. And I'm also the award, have won the 1991 Westinghouse Award for Business Development. I don't say that to brag about myself, but I want to point out I have a background in these three areas. One of the things I want to challenge you a little bit on is your first statement that says we have to develop this consensus of our organizations about how we perceive and how we want to put forth our expectations on low-level radiation to the public, to the regulators, to those people that pay the bills. I think I want to challenge that. And I want to challenge that because there are two things that are going to be much more difficult than to us coming to consensus. The first one is the cultural development, the cultural shifting of people to accept any kind of consensus law is going to take much, much longer than we're going to have to do, and we need to start now. I'll remind everybody of the old BRC, below regulatory concern, how successful that was when we're out there. Well, that's because we do not have the expertise on understanding how to propagate new concepts out into the cultures. We need to start working with other groups to start working on that now. Second point is a little bit on the craft side.
If you can move along, because we're now
Thank you.
we have infringing now.
We do have to talk about economics. We do have to talk about business development. I have worked very hard on this site to get away from the concept of ALARA as a terminology and start talking about optimization. So we can really start looking at cost-benefit analysis. Right now, our costs are crazy high here at the site relative to the risk we're taking. So that's my challenge to you folks.
Very good, thank you. Those are really good points. Dr. McClellan did mention public right at the get-go, and I know that that's very vital. We have a lot of good beginnings of discussions here. I think we should continue them now at the coffee break so that we stay on schedule and then come back promptly. I really appreciate Drs. Brennan and McClellan in getting us off on the right foot. Thank you very much.